Hi and welcome to this second video about Apache Spark shuffle writers, and this time we will focus on bypass merge shuffle writer. So as last time, I will show you three different codes that will use or will not use this kind of shuffle writer, this type of shuffle writer, and the first one will use it. And there are two important properties to remember. The first property is the property defining the number of mapper tasks, which will be 3, and the second one is the property defining the number of shuffle partitions, which is 2 in this example, and which has to be lower or equal to bypass merge threshold, which is set here to 10. By default in Spark 3.0.0, both are defined both are set to 200. So the code is very straightforward. I'm doing a sample mapping. So first I'm creating my dataset composed of user case class, and later I'm doing group by key that will transform a bit all the users. But the processing is not very important. Most important thing are these two properties I explained before. So I will run the code, and I will also show you what are the shuffle files generated on my local file system. But first, as you can see, the condition here will evaluate to true since the number of shuffle partitions is lower or equal than the bypass merge threshold. So we are of course using an appropriate shuffle handle, and we are creating a corresponding shuffle writer. So we are doing that for the map task, and now we are working on the map ID 1, which is the mapper and the second map task. And the logic of the algorithm is that it starts by creating the files for both shuffle partitions per mapper task, and later adding the records to the file corresponding to the shuffle partitions within this mapper task. And everything happens in the location managed by the block manager, which is this one. So let's see what we have inside. We have nothing. That's normal. We are just initialized the writers, the buffers, or the streams, and we will write the data only later in this part that I will skip for this demo because it's not very important. In a nutshell, we'll use the iterator method has next to verify whether we have or not more records to process. We will retrieve the record with the next method, and later we will compute the number of shuffle partitions by calling getPartition for the key, and we will writing the key and the value to the corresponding file. So we are still initializing, and as you can see, we are already processed the records, and let's see what we have inside. We have, as you can see, 2 shuffle files per mapper task. Since we have 3 mapper tasks, we should have 6 files, 6, and it's marked here as well, which means that we correctly executed this algorithm, and now we are confirming the writes. We are flashing the accumulated records, remaining records to the temporary files, and by the end, more exactly in this step. So now I think we are doing that for other map. Yeah, map first, this third one, and we have still 6 files. Okay, and now we will start to generate the shuffle data and the shuffle index files. So as usual, we are using the local shuffle disk writer, which is the default one, but as you know, starting from Spark 3, I think we can customize this part because they are implemented with this interface and this one for the writer. But that's not the topic of this demo. Let's go back to our BypassMergeSortWriter that generates the final files in this method. And the generation consists on merging all these temporary files to the data file and at the end generating the index file to indicate to the reducer where it can find the data it needs. So yeah, and we are doing that here for every shuffle partition. And we are doing this, of course, for every mapper task. So as you can see, we are already cleaned some previous data generated by the mappers. And now we are still one file left. Yeah, and now we will do the final commit, which will create the index file. Let's check. Okay, we have the data. We will commit the data approximately. Yeah, so we have the final data and corresponding final index file to it. So that was the first demo. And now we'll see the result. So that was the first. The second, so in this second demo, I will show you that we cannot use bypass merge where if we have some map partial aggregation, so the aggregation which is pre-compute partially on the mapper side and which is later combined in the reducer. And here you will see that I'm using a tree reduce operation of old RDD API, doing this partial aggregation thing. And as you can see, this condition will not hold. So obviously we will use the sort shuffle writer. Yeah, that's not the goal. I will skip this part. And last example, I will do the group by key on top of RDD, and I'm wondering if you know what will happen. So maybe your first reflex, if you know only the dataset API, will be that it will also skip the bypass merged writer, but I will prove you that it will not be the case. So as you can see here, we are going to the pair RDD functions that call under the hood the combine by key method by defining the map site combine flag. By default, this flag is set to true and it changes only for the group by key operation, simply because the group by key operation in RDD doesn't work the same as for dataset. Namely, it groups all the data to the partitions, to the shuffle partition, and performs the final aggregation here. It's not the case for Spark SQL for dataset abstraction, where this operation can performs some partial aggregations. So does the map site combine? So does the RDD's map site combine on the mapper sides, and that's the reason you can see that the map site combine for this RDD abstraction is set to false. So globally, it will not skip the bypass merge sorter, and since the number of shuffle partitions is lower than the number of bypass merge threshold, we will use bypass merge shuffle writer. And globally, that's all for this bypass merge sort shuffle writer. And in the next video, I will show you an example of the last shuffle writer, which is called Unsafe Shuffle Writer. And of course, you will find a corresponding blog post in the description of this video. It was Bartosz Konieczny from waitingforcode.com. Thanks for watching.